Welcome to MAI 580. This is a course about agentic AI, systems that do more than produce text. They can gather evidence, use tools, maintain state, plan, and be evaluated. Before we build any of that, we need a shared mental model of the language model at the center. Today is not a history lecture. It is the foundation for every design decision we will make later.
This is a graduate, applied course, so our rhythm is always the same. Understand a concept, implement a small version, inspect what the system actually did, and defend the design. The why is important. A convincing demo is not enough for an agentic system. You must be able to explain its evidence, cost, failure modes, and safeguards. The who is you as an engineer and evaluator, not simply a user of an API. Our objective has 4 connected parts. First, analyze the LLM and understand its trade-offs. Second, design systems around it with tools, retrieval, and memory. Third, evaluate the system using evidence. Fourth, deploy it responsibly. These 4 parts are exactly the 4 course learning outcomes on the slide. Now read the line at the bottom, because it is a course policy and not a decoration. These are not separate units. It is tempting to treat evaluation as something we add at the end, and security as something another team handles. In this course, that separation is not allowed. Let me explain why, using 3 failures you will actually meet. A system can be clever, but unsafe. It gives an excellent answer, and it also sends private data to an external service. A system can be safe, but unhelpful. It refuses every request that carries any risk. A system can appear useful, but be impossible to evaluate. It produces a convincing demonstration, and nobody can say how often it is wrong. None of those 3 is a complete project. As a consequence, when you defend your project, you will be asked about all 4 parts, not only the part that worked. The order is deliberate. We first understand the reasoning substrate. Then we give it reliable evidence and actions. Then we organize autonomy. Finally, we test and govern it. Look at the 4 blocks. Block 1 is the reasoning substrate. Today's foundations, then reasoning, prompting, and context engineering. Block 2 is acting with evidence. Tools, function calling, and the model context protocol. Then grounding and memory. Block 3 is autonomous design. Architectures and planning, multi-agent orchestration, and emerging paradigms. Block 4 is proving and governing. Evaluation, observability, and debugging. Then security, safety, and responsible deployment. This order prevents a common mistake. A team reads about a multi-agent framework and starts there. They build 5 agents that talk to each other. Then the system fails and they cannot say which agent was wrong. They never asked whether one model, one tool, or a better retrieval pipeline would have solved the problem. As a consequence, we build the substrate first. For the first 5 weeks, we build the foundations. These are also the topics the midterm assesses. Look at the table row by row. Weeks 1 to 5 cover foundations, context, tools, grounding, and memory. Lab 1 runs early, and both the project proposal and Lab 2 are due in Week 5. Weeks 6 and 7 move to single-agent architectures, planning, and frameworks, and Lab 3 is released. Week 8 is the midterm, covering topics 1 through 5. Weeks 9 to 13 cover multi-agent systems, emerging paradigms, evaluation, and security. In that period, you also present a paper seminar and take part in a red team exercise. Weeks 14 and 15 are project presentations with a live demonstration and questions. Then the comprehensive final. 1 practical instruction. The detailed dates, deliverables, grading policy, attendance, and academic integrity rules are in the syllabus on e-learning, not on this slide. Check it before every class because the calendar may adapt as the field moves. And start thinking about a project problem now, because a good project needs a real question, not a flashy interface. Notice what we reward. 20% is sustained preparation. quizzes, assignments, paper reading, and seminar activities spread across weeks 2 to 13. 25% is the midterm in week 8. 25% is the course project. 30% is the comprehensive final examination. Now, read the box at the bottom because it defines what project means here. You will work in teams of 2 or 3. You will build, evaluate, and defend an agentic system. The grade depends on 6 things: technical depth, evaluation rigor, failure analysis, security and safety treatment, report quality, and the live defense. Notice what is absent from that list. Whether the demonstration works is not one of the 6. A demonstration that works once is not evidence. It is a single sample. As a consequence, a team that reports honest failures and measures them will score higher than a team that shows a polished demonstration and cannot explain when it breaks.
Today has one argument. Read the sentence at the top of the slide. This course is about systems that act. But an agent is a loop wrapped around a language model, and you cannot reason about the loop without understanding what sits inside it. So the lecture has 2 halves. The first half is the substrate. We open the model, self-attention refreshed, then how a transformer becomes a language model, then the architecture frontier from 2023 to 2026. The second half is the gap. We ask what language models structurally cannot do, what that means for ethics, safety, and risk, and why agents and tools follow from it. The conclusion is printed at the bottom, and it is the thesis of the whole course. Agents are not a product feature. They are the engineering response to a specific, well-documented set of limitations. One request while you listen. Listen for the word because. Every component we introduce later must have a reason to exist.
These are today's learning outcomes, and they are written as things you will be able to do. First, explain how self-attention, causal masking, and the decoder block turn tokens into a language model. Second, distinguish 3 things that are often confused: training time scaling, inference time compute, and architectural efficiency trade-offs. Third, identify which failures are structural, rather than failures that more scale would remove. That third outcome is the hardest, and it is the purpose of the second half of the lecture. Fourth, justify tools, memory, verification, and agent loops as engineering responses to those failures. Fifth, describe why autonomy changes the security and ethical stakes of an AI system. Now, read the connection to the course. This lecture establishes CLO 1, which is analysis. The remaining topics build what CLOs 2, 3, and 4 require: the designs, the evaluations, and the safeguards. Today we analyze because we cannot design what we have not analyzed. We begin with the mechanism. The key question is simple. When a model reads a token, how does it decide which earlier tokens matter right now? The transformer paper is old by the standards of this field, but the core mechanism still sits inside most frontier language models. Look at the 2 columns. On the left, the original paper from 2017. The base model had 65 million parameters. The big model had 213 million. It was trained for 3.5 days on 8 GPUs. On the right, a frontier model from 2026. 2.8 trillion total parameters, about 104 billion activated for each token, and a context window of 1 million tokens. That is roughly 13,000 times larger. Now, read the note at the bottom, because it is the reason we are here. The main operation is still a weighted average of vectors, and the weights still come from dot products. What changed is the scale, the data, the training procedure, and the engineering required to control cost. So we revisit attention, not for history and not for nostalgia. We revisit it because its cost is a systems constraint you will meet in your own project this semester. Let us start with the problem before we name the mechanism. Consider the word bank. Look at the 2 sentences on the slide. In the first, I sat by the bank of the river. In the second, I deposited cash at the bank today. The same 5 characters appear in both sentences, but the meaning is different. Now, state this as a problem the model must solve. The same 5 characters must become 2 different vectors, and the only information available to tell them apart is the surrounding text. In the first sentence, the useful evidence is the word river. In the second, it is the words deposited and cash. Notice that this evidence is not at a fixed distance from the word bank. So what must the mechanism provide? The slide names 3 requirements. First, every position can look at every other position with no fixed window. Second, the amount of looking is learned and content dependent, not positional. The model does not always look at the previous 3 words. It looks where the current input suggests it should look. Third, it must be parallelizable. A recurrent network processes one position after another, and that sequential dependency was the bottleneck that attention was invented to remove.
Use the database analogy because it makes the 3 roles intuitive before we see the equation. A hash table matches a key exactly and returns one value. Attention does the same 3 jobs, but softly. The match is a similarity score instead of an exact test, and the result is a mixture of all the values, weighted by that score. Now look at the 3 projections. The query asks, "What am I looking for?" The key advertises, "What do I offer?" The value carries, "What do I pass on?" Each one is the input multiplied by its own learned weight matrix. Now the question in the box, and it is worth answering carefully. Why are keys and values separate objects? Because what makes a token findable is not what makes it useful. Take the example on the slide. The capital of Saudi Arabia is, and then a blank. The token Saudi is findable because it is a country name next to the word capital. That is its key. What it should contribute to the prediction is geographic content. That is its value. Separating them lets the model optimize findability and usefulness independently. This is not a literal database, but the 3 roles are exact.
Now name the equation, but do not treat it as something to memorize. Read it as 3 steps. Step 1, Q times K transpose. This computes all the pairwise similarities between queries and keys. The result is an n by n matrix, where n is the number of tokens. Remember that shape, because in 2 slides it becomes our cost problem. Step 2, the softmax. This turns the similarities into weights that are never negative and that sum to 1 in every row. So each position produces a proper weighted average, not an arbitrary sum. Step 3, multiply by v. We use those weights to combine the value vectors, and that weighted average is the output. Now, one addition that this equation does not show, and it is essential for a language model: causal masking. When we predict the next token, position 5 may use positions 1 to 4, but it must not see position 6. Without the mask, the model can see the answer it is being asked to predict. With the mask, generation is legitimate. We return to the mask shortly because it is also the origin of the statelessness we meet in section 4.
Walk through one row only. First, a query scores each key. Second, higher score means greater relevance. Third, softmax turns relative scores into a distribution. Fourth, we multiply each value by its weight. Fifth, we sum. Ask if the token it is being interpreted, which earlier noun should get the largest weight? The numerical example is there to make the flow concrete, not to test arithmetic. Here is a question worth getting right. Why divide by the square root of dk and not by dk itself or by the logarithm of dk? The slide gives the actual argument. Take a query and a key whose components are independent with mean 0 and variance 1. Their dot product is a sum of dk such terms, so its variance is dk. The standard deviation is therefore the square root of dk. Dividing by the square root of dk is exactly what restores unit variance. It is not an arbitrary choice. Now the consequence of removing it. As dk grows, the scores spread out. The softmax saturates towards 1 hot. Its gradient becomes very small, and training stalls. Now read the key point, because it generalizes beyond this formula. This is a numerical stability fix. It does not explain language or meaning or cognition. Much apparent architectural complexity is engineering that helps an optimizer work reliably. So when a paper explains why an architecture works, ask one question. Does the explanation describe a mechanism, or is it only a story?
One attention operation computes one kind of relationship, but language needs several at the same time: syntactic agreement, co-reference, topical association. So instead of one wide attention, we run several narrower ones in parallel. Look at the equation. Each head applies attention with its own query, key, and value projections. Then we concatenate the head outputs and multiply by one output matrix, WO. Now, the 2017 configuration on the left, because the numbers make it concrete. The model dimension was 512. There were 8 heads. So dk and dv were 512 divided by 8, which is 64. Each head is narrower, so the total cost is comparable to a single wide head. We get several relationships for roughly the price of one. One caution: do not claim that every head has a clean human label. The model learns them, and many heads are not interpretable. The capacity for different relations is the point, not a tidy naming. Now, read the right-hand column, because it is a forward reference. Heads are the unit that later architectures attack: grouped query attention, multi-head latent attention, and key value sharing across heads. Every one of those is an attempt to shrink the same thing, the KV cache. This slide makes the previous idea visual. Each projection matrix sends the same token into a different and narrower subspace. Look at what that buys us. One head can specialize in syntax, while another tracks co-reference, and neither has to compromise, because they never share a representation. That last clause is the important one. If all the relations had to live in one space, improving one of them would damage another. The head outputs are combined only at the end, before the next stage. Now, the connection to agent design, because this is not only a modeling detail. A language model is not retrieving a single fact from a single location. It is continuously constructing context-sensitive representations. As a consequence, when your agent produces a wrong answer, there is usually no single place inside the model that you can go and repair. We have the mechanism. Now ask the systems question. What does it cost to use it repeatedly? A decoder block repeats 2 kinds of mixing, and the slide separates them clearly. Read the first block. Attention mixes across tokens. Every position gathers from every earlier position. This is where context enters the model. Now, the second block. The feed-forward network mixes within a token. It is applied identically at each position, and it holds most of the parameters. Remember that, because it also holds most of the stored knowledge. So we have a useful division of labor. Attention brings in context. The feed-forward network transforms what is already there. Around both, residual connections preserve useful information, and normalization keeps training stable. Stack this block many times, and the model gains depth. Now read the third block, the one marked in red, because it carries the most weight for this course. Position T may attend only to positions up to T. Without the mask, the model sees the answer. With the mask, we get autoregressive generation, and the same mask is the reason for the statelessness we will meet in Section 4. One design choice produces both the capability and one of its main limitations. This figure carries an inequality, and I want you to leave the room with it. As the context length grows, full attention compares every pair of positions. The number of pairs grows with the square of the sequence length. So attention gives quadratic pressure in time and in memory, while the feed-forward part grows only linearly in the sequence length. Now look at where the 2 curves cross. For short sequences, the feed-forward network dominates the cost, and attention is cheap. For long sequences, attention dominates, and it dominates quickly. Now the conclusion, and it is the sentence that runs the rest of this lecture. Long context is not free capability. It is a choice that spends compute and hardware. We will meet this same pressure twice more today. First in the KV cache on the next slide, then in the whole architecture frontier of Section 3. Almost every architecture we discuss later is an attempt to move this crossing point. During generation, we do not recompute the keys and values of every previous token at every step. We cache them. Look at the effect written on the slide. Work that was order T squared, repeated at every step, becomes order T. That is a large saving, and it is the reason generation is affordable at all. But now read the price. The cache costs memory proportional to n, the sequence length, times L, the number of layers, times H, the number of heads, times D head, the dimension of each head. Now the word printed in bold, which is the part people forget. This memory is not shared between requests. Each concurrent user holds their own cache. So the memory bill grows with the number of users as well as with the length of their contexts. Now the final sentence, and I want you to remember it in exactly this form. An agent's context is its working memory, and the KV cache is the bill for it. This is why long agent traces are a systems problem and not only a design preference. Every tool output your agent appends is memory that some server must hold. This is an operations picture. A shared fixed prompt prefix can be cached and reused. Each user's new tokens then add private cache state. This is one practical reason to keep stable instructions and tool schemas at the front of a prompt. Prompt structure affects both reliability and serving cost. Let us check the first learning outcome using the two columns. On the mechanism side, 3 statements. Attention is a learned, content-dependent weighted average. Multi-head attention runs several such averages in parallel subspaces. Attention mixes across tokens, while the feed-forward network mixes within one. On the economic side, attention is order n squared in time, and the KV cache is order n in memory. As a consequence, long context is a cost problem before it is a capability problem, and agents generate long contexts by construction through messages, retrieved documents, and tool outputs. So this is not only a problem for model providers, it is your problem. Now, the last item, and it is the practical one. Providers cache and share identical prefixes, so keep the front of your context fixed. Hold that line. We come back to it in Section 3 with 2026 numbers attached. Now we turn the decoder mechanism into a language model, then connect its training and use to real resource budgets. This is the transition in one picture. Repeated decoder blocks learn to predict the next token. Scale and data turn that simple objective into surprisingly broad behavior, but the objective itself remains simple. The training objective is next token prediction. Stated precisely, maximize the probability of the next token given the previous tokens. That is the whole objective. Now, notice what is absent from it. The model is not explicitly trained to be truthful. It is not trained to be safe. It is not trained to be goal-directed. It is not trained to use tools. It may acquire useful behaviors as a consequence of the data and the scale, but those are consequences, not guarantees. This distinction matters for the rest of the course. When a system behaves well, we should ask whether that behavior was trained or whether it merely appeared. Trained behavior is more reliable. Behavior that merely appeared can disappear when the input changes. And this gives us a recurring project question, which you should ask yourself by week 5. Does this task truly need an agent, or would an ordinary software workflow be better and more predictable? Here is a distinction that explains something you have all experienced. In training, we already know the complete text sequence, so many positions can be processed in parallel. The model predicts the token at every position at the same time, and the causal mask stops it from cheating. In generation, this is not possible. Token 20 depends on token 19, which depends on token 18. Each token must be produced before the next one can start, so generation is sequential by construction. Now the familiar experience. A model can read a long prompt quickly and then stream a long answer slowly. Reading is parallel. Writing is not. And notice the consequence for agents. An agent that produces long outputs or that runs many steps pays this sequential cost at every single step. We will name these two phases more carefully in a moment as prefill and decode. In-context learning means the model adapts its behavior from examples and instructions placed in its current context, without changing its parameters. Look at the left column. GPT-3 in 2020 had 175 billion parameters, but the finding that mattered was not the size. It was that a task could be specified by examples in the prompt with no gradient update at all. Nothing was trained. The behavior was requested. Now read the right column, because this is why you care. Every tool description you write this semester is in-context learning. You are teaching the model an API at inference time, in prose, with examples. That is the whole mechanism. There is nothing else happening. Now the uncomfortable corollary at the bottom, and I want you to take it seriously. If tool use is in-context learning, then a badly written tool description is a badly posed learning problem. The model will then fail in the same way a student fails an ambiguous exam question, not because it is incapable, but because the question was unclear. In Topic 3, we treat tool schemas as an interface design problem, and this slide is the reason why. This is, in my view, the most important figure in the lecture, so read the axes carefully. The x-axis is how many examples you put in the prompt. The three curves are three different model sizes. Now follow the 1.3 billion line. It is almost flat. More examples by that model, almost nothing. Now follow the 175 billion line. It climbs steeply. Same prompts, same examples, very different response. So here is the conclusion. The ability to learn from the prompt is itself a capability that appears with scale. And notice that no weights changed anywhere in this figure. Every tool description and every few-shot example you write this semester rides on that upper curve. But do not convert this into magic. In-context learning is still bounded by the context length, by the clarity of your prompt, and by the model's ability to follow instructions. It is adaptation in the prompt. It is not persistent learning. The model remembers nothing after the request ends. Before discussing scaling laws, we need a vocabulary for what exactly gets spent. Before we discuss any budget, we must distinguish the quantities being budgeted. They measure different things, and they must never be added together. Read the table row by row. Parameters are a count of weights. They describe model capacity, and they are often reported as 7 billion, 70 billion, or 1 trillion. Tokens are pieces of text. They are the basic unit of input, output, context, and API billing. A flop is one arithmetic operation, one multiply or one addition. It is a very small unit of computation. Flop per second is hardware speed, or throughput. 1 teraflop per second is 10 to the 12 operations per second. Bytes and gigabytes measure memory capacity, that is, the data held right now, the weights, the activations, and the KV cache. Now the line at the bottom, which is the one to remember. Flops measure work. Gigabytes measure space. Seconds measure waiting. These are three different constraints, and an engineering design must satisfy all three. A design that is cheap in compute can still fail because it does not fit in memory. Students often say word, but the model does not process words. It processes tokens. Follow the diagram at the top. Text goes into a tokenizer, which produces tokens. The tokens go into an embedding table, which produces vectors. Now the left block. A token is not a word. Tokenizers split text into reusable pieces. One word may be one token or several. Punctuation, code, Arabic, and other languages can produce very different token counts for text of the same visible length. This is not a small detail for this class, because several of you will build agents that work in Arabic. Now, the right block, which is why this changes engineering decisions. Context windows, KV cache memory, training data, rate limits, and API invoices are all measured in tokens, not in words, not in pages, not in characters. Now, the instruction at the bottom. Treat a reported 1 million token context as a capacity in the model's own units.
Always measure the actual tokenizer count before you design a budget. Token budgeting is a real engineering task, not formatting.
Parameters are stored numbers, and storage depends on precision. A rough 7 billion parameter model needs about 28 gigabytes in FP32, 14 gigabytes in FP16/BF16, 7 gigabytes in int8, and 3.5 gigabytes in int4, before other runtime overhead. Quantization stores weights with fewer bits. Why do it? Lower memory footprint and lower bandwidth demand can make deployment feasible. The trade-off is possible loss of quality or numerical robustness. Also, distinguish model weights from KV cache and activations. A model that fits in memory may still fail on a long context.
Think in 3 budgets: training compute, serving compute, and serving memory. Training compute constrains what model can be built. Serving compute constrains latency and cost per request. Serving memory constrains concurrency and context length. If a system is slow, the cause may be sequential decoding. If it crashes under load, the cause may be cache memory. If it was never trained well, the cause is neither. Diagnose before optimizing.
Inference has 2 phases, and the slide separates them because they behave differently. Read the left column. Prefill reads the prompt. The model processes the input context. Many input token operations can be parallelized on the GPU, so this phase is often measured by input throughput. But a long prompt still costs compute, and it builds a larger KV cache. Now, the right column. Decode generates the response. The next token depends on the previous one, so generation is sequential. 1,000 reasoning tokens require roughly 1,000 successive decoding steps. This phase usually determines the time to the last token. Now read the small table because it gives you the design rule in one view. A longer input means higher prefill cost, a larger initial KV cache, and a slower first token. A longer reasoning output means more decode steps, a cache that continues growing, and a slower final answer. As a consequence, when someone says make the model think longer, they are choosing the second column. It has a real and predictable cost. Agent loops must spend tokens deliberately.
Now, let us follow one single agent request through the system, using the diagram. On the left, an input of n tokens. The model reads the context. That is prefill. It stores keys and values into the KV cache. Then it generates m tokens, one step at a time. And notice the label on the cache. It grows with every token. Now, the 2 blocks below, on compute and time. Reading the prompt costs computation, and generating output costs 1 sequential model step per token. So more reasoning tokens or more tool loop iterations mean more compute and more latency. On memory, the model weights are shared between all requests, but the KV cache belongs to this request alone, and it grows with n plus m. As a consequence, long contexts reduce how many requests one GPU can serve at the same time. Now, the line at the bottom, which separates 2 ideas we are about to compare. Scaling laws plan a training compute budget. Test time compute chooses how much work one single request deserves.
Here is the concise model, and it is worth memorizing the 3 rows. First budget, training data and compute. It is spent before deployment, and it changes what the model learns, that is, its weights. Second budget, model capacity. It is chosen before deployment, and it changes how much the model can represent. Third budget, test time compute, also called inference time compute. It is spent while solving one request, and it changes how much effort the same trained model spends on that request. Now read the warning box, because the terminology confuses people every year. Test time is historical terminology. Nothing is being tested. It means the computation used when a deployed model answers a real question. It has nothing to do with model evaluation. We will say inference time whenever that is clearer. Use this analogy carefully, because it is accurate only if you keep the two sides separate. Training is studying. More books, more worked examples, more practice before the exam. This changes what the student knows. And here is the important part. When the exam begins, that preparation is fixed. Nothing more can be added. Inference time compute is exam time. More time to plan, to try an approach, to check the arithmetic, to notice an error, and to revise. Notice what does not happen. The student learns nothing new during the exam. They use existing knowledge more thoroughly. Now, the line at the bottom, which converts the analogy into engineering. A long reasoning trace, a second attempt, or a tool call followed by a reconsideration are all forms of spending more inference time compute. These are different levers. And as an agent designer, during a request, you can only choose the second one.
Let us be precise about what loss measures because it is often overinterpreted. For each next token, the model assigns a probability. Loss is the average penalty when the correct token received a low probability. So lower loss means better next token prediction on a held-out distribution. Now, the two columns and the contrast is the point. On the left, what a scaling law predicts, a smooth reduction in validation loss as parameters, training tokens, or compute increase. That is a useful engineering signal. On the right, what it does not promise. It does not promise a proportional increase in benchmark score, factuality, tool use, safety, or agent reliability. Those depend on the task, on post-training, on prompting, and on evaluation. Now, the line at the bottom, and it is deliberately two-sided. A small change in loss can sometimes unlock a visible capability and can sometimes barely affect the task you care about. So measure the actual task. If your project claims an improvement, show success rate, cost, latency, and robustness, not only a generic model metric.
Let us start with the plain observation. A bigger model, trained on more data, usually performs better. A scaling law turns that observation into an empirical budget planning rule. You fit a curve to experiments you can afford, and then you use it to estimate what a larger run is likely to buy. Now, the training side quantities on the left. N is the number of parameters, the model size. D is the number of training tokens, the data. C is the training compute in flops, which is the money. And they are not independent. Roughly, C is about 6 times N times D. Now, read the right column as a budget constraint, because that is what makes it interesting. C is fixed. It is your GPU allocation. So doubling the model size halves the training data you can afford. There is no way to avoid that choice. This is what makes "how should I split my compute" a real engineering question. Now, the idea to retain at the bottom. More resources bring real and predictable improvement, but each extra improvement costs more than the previous one. The log-log plots and the exponents are evidence for that claim. You do not need to memorize the formula.
Now, the evidence. And I want you to read the shape rather than the exponents. Look at the axes first. Both axes are logarithmic, and the points fall on a straight line. That is the entire claim of this figure. 3 separate resources, compute, data, and parameters, each give a straight line over many orders of magnitude. That regularity is remarkable, and it is what makes planning possible. Now, look at the slope, because the shallow slope is the important part. The line rises, but it rises slowly. Doubling a budget helps, but it does not double performance. This is exactly why larger training runs become so expensive. Do not memorize the exponents on these plots. Different papers fit slightly different numbers, and those numbers move. Remember the shape. A straight line on a log-log plot with a shallow slope. Straight means predictable. Shallow means expensive.
Let us state the consequence of that shallow slope directly. The fitted curves improve steadily, but each additional improvement requires disproportionately more data and more compute. Now read the 2 columns together, because both are true at the same time. The good news?
Scaling is reliable enough to plan around. More data and compute generally yield a better model, rather than a random outcome. For an engineering field, that predictability is valuable. The hard news? The gains diminish. A small improvement at the frontier can require orders of magnitude more money, data, and energy than the previous improvement did. Now the line at the bottom, which explains the economics of this whole field. The gains are real, they are predictable, and they are extremely expensive. And that last word is the reason for the next section. Because training scaling became so expensive, inference time compute became an important additional lever.
This slide is a good lesson in how an empirical field corrects itself, so read the two columns as a sequence. On the left, Kaplan and colleagues in 2020. Their recommendation was to spend most of any compute increase on model size, make the model much bigger, and let the data grow more slowly. On the right, Hoffman and colleagues in 2022, the Chinchilla paper. Their finding was that the earlier recommendation was wrong. N and D should grow at the same rate, roughly 20 training tokens for every parameter. Now read the practical lesson at the bottom carefully, because it is easy to draw the wrong conclusion. At the same training budget, Chinchilla used a smaller model and trained it on much more data. It performed better. But the reason was that the earlier model was undertrained. It was not because smaller models are intrinsically superior. The lesson is not a number. The lesson is to allocate a fixed budget deliberately.
This figure visualizes why two influential recommendations appeared to disagree. They asked related but not identical questions and used different assumptions. Treat research numbers as scoped evidence. Ask what was measured, under which regime, and what decision the result really supports. The transferable lesson is disciplined measurement. There is no universally optimal model-to-data ratio that can be copied into every project. Your project will have the same logic at a smaller scale. Define the budget, select the metric, run a controlled comparison, and explain the trade-off. Now let us check the theory against real 2026 systems, because this is where the recommendation breaks. Look at the table. DeepSeek V4 Pro, 1.6 trillion total parameters, but only 49 billion activated per token, which is about 3%. V4 Flash, 284 billion total, 13 billion activated. Kimi K3, 2.8 trillion total, 104 billion activated. Notice the pattern in that activated column. Almost every frontier model now activates a small fraction of itself. Now do the arithmetic in the left box. Chinchilla said about 20 tokens per parameter. Take V4 Flash, 32 trillion tokens divided by 284 billion parameters is about 113. That is roughly 5 times the recommendation. And measured against the parameters actually active per token, 13 billion, it is about 2,500. Now the right box explains why. Compute optimal is not the same as deployment optimal. Chinchilla asks for the cheapest way to reach a given loss. Industry asks for the cheapest way to serve a given quality, forever. Training is paid once. Inference is paid on every request. So you deliberately overtrain a model that is small at inference time. We now return to the exam time lever. What can a fixed model do if we allow it to spend more work on one hard request? Inference time compute, sometimes called test time compute, is extra computation after training is finished. It can mean generating candidate solutions, using a verifier, decomposing a problem, searching, calling tools, or reflecting on a result. The weights are fixed. The trajectory gets longer or better structured. The design question is not can we make it reason, but what extra work produces enough reliability to justify its cost? The study and exam analogy has a direct engineering consequence, so let us make it explicit. Axis 1 is studying more. More hours, more books, more practice problems, all before the exam. And when the exam starts, that investment is fixed and cannot be changed. Axis 2 is more time in the exam, Time to try an approach, notice that it fails, back up, check the arithmetic, and try again. Notice the sentence in the second column. The student has learned nothing new. They are using what they already know more thoroughly. Now, the line at the bottom, which connects this to what you will build. A model that writes a long chain of reasoning before answering is doing the second thing. And so is an agent that calls a tool, reads the result, and reconsiders. Your agent loop is axis 2. Every extra iteration you allow is exam time that you are buying. Now, let us see why this is genuinely a second axis, and not just a way of describing the same thing. Start with the sentence at the top. Compute per token is fixed by the architecture. What is 2 plus 2? And prove this theorem cost exactly the same per token. But compute per question is not fixed. Read the box. Emit 3,000 reasoning tokens instead of 10, and you have run 3,000 forward passes on that question instead of 10. That is roughly 300 times the computation. Same weights, no retraining. Sequence length is the dial, and it turns per request. Now, the table compares the two axes on 5 points. What you increase, parameters and training tokens, versus tokens generated per question. When it is paid, once before release, versus every request, forever. Who pays? The lab that trains it, versus whoever calls the API, which is you. How it is controlled? Fixed at training time versus per request at runtime. Does it adapt to difficulty? No versus yes. And what limits it? Data, money, and hardware versus latency, the context window, and your budget.
Now the evidence from two laboratories that reached the same conclusion independently. On the left, DeepSeek R1. Reasoning was elicited by large-scale reinforcement learning on a strong pre-trained base, not by making the base model bigger. The capability was already latent, and the reinforcement learning taught the model to spend tokens using it. On the right, Kimi K1.5 and K3, same conclusion, reached separately. K3 states it directly. The rise of reasoning models has established test-time computation as a second axis of scaling. Now the two consequences for you, and the second one is the one to remember. As an engineer, when a frontier lab says it is investing in test-time compute or in long-horizon tasks, it is investing in exactly the workload you are about to build. As someone with a budget, Axis 1 is somebody else's capital expense. Axis 2 is your invoice on every request for the life of your system. A reasoning model spends extra compute inside one response. An agent spends it across 40. This is the figure I would ask you to remember from this section. So read the two panels together. The left panel shows AMI accuracy during reinforcement learning. It rises from 15% to 77%, and it crosses the green dashed line, which is the average human competitor. The right panel shows the average length of the answers over the same training run. It goes from a few hundred tokens to more than 10,000. Now the sentence that matters. Nothing in the reward asked for longer answers. The reward asked only for correct ones. Thinking longer is the strategy that the model discovered by itself. This is the strongest evidence that test-time compute is a real axis and not a prompting trick. If longer answers were only a stylistic habit, they would not appear when the objective rewards correctness alone. We know the pressure. Attention and cash cost. This section asks how current architectures buy more useful context and capacity for the same budget. Keep one organizing claim. The frontier is mostly an economic story. Architectures differ, but their practical purpose is to reduce memory movement, avoid unnecessary attention, increase capacity without activating all of it, or make long context affordable. Flash attention is, for an engineer, the most instructive result in this section, and the reason is on the slide. Nothing changed mathematically. It is identical attention, producing identical outputs. What changed is the scheduling. The computation is tiled so that the n by n matrix never has to reach high bandwidth memory.
Now think about what that tells us. If rearranging the memory access gives a large speedup while the arithmetic stays exactly the same, then the arithmetic was not the bottleneck. The real bottleneck was memory bandwidth, that is, moving data. This is a lesson that goes far beyond attention. A theoretical operation count is not the whole performance story. Data movement and hardware layout matter, often more. So here is the practical rule for your project, written at the bottom of the slide. When your agent is slow, suspect data movement first.
There are two broad choices: attend selectively or replace part of the attention mechanism with a compact recurrent state. Sparse attention starts from a simple question. Does every token really need to compare itself with every other token? Sparse attention answers no. A pattern may focus on local neighbors, on a few selected global tokens, or on blocks. The benefit is a lower cost at long sequences. The risk is missing a relationship that falls outside the allowed pattern. So it is a trade-off: efficiency against universal access to the context. Now read the 2026 result at the bottom, because you should not skip it. Sparse attention is widely deployed in long context serving stacks, yet no framework audits how discarding blocks changes the influence of specific content. Read that again. It is deployed widely, and its effect on specific content is not audited. Now, the consequence for your project. A vendor's advertised context length is not a promise that everything inside it is actually attended to. If your design depends on a detail buried in the middle of a very long context, test that assumption. Do not assume it. Let us build the mechanism one step at a time, following the diagram. A state space model reads one token at a time. It folds that token into a fixed size state. Then it reads the output features out of that state. Now notice the word fixed. The state is updated, never expanded. And that is the whole reason the memory does not grow. Compare this with attention. Attention keeps every previous token available, so its memory grows with the sequence. A state space model keeps a summary of fixed size, so its memory does not grow at all. Here is an everyday picture of the same idea. Attention is like keeping every page of a book open in front of you and rereading whichever pages you need. A state space model is like taking notes as you read, and then answering from your notes. Both can work, but notice where the difficulty moves. If you carry a summary instead of the original text, then the quality of the summary becomes the central question. Anything the summary dropped is gone, and no later step can recover it. This is the honest comparison, and I want you to hold both sides. Standard attention keeps everything. It preserves direct access to individual past tokens, and it pays more as the context grows. A state-based approach keeps a summary. It is cheaper, but it must compress history. Neither one is automatically superior. The correct choice depends on the task. Does the task need exact retrieval of a distant detail, or can it rely on a learned summary? Now, read the two notes at the bottom, because they correct a common impression. Selectivity, which means making the state update depend on the input, is what made state space models competitive and not merely cheap. Before selectivity, they were fast and weaker. And then Mamba 2 showed something stronger. Transformers are state space models. That result is a unification, not a competition. The two families turned out to be two views of one underlying structure, which is why they can share kernels and theory. Now, let us look at what the frontier is actually buying, with real numbers. Read the two panels. The top panel is flops for one token, plotted against position in the context. The bottom panel is KV cache in gigabytes, plotted against sequence length. The dashed gray line is V3.2, the previous generation. Notice that both quantities grow linearly with context. That is the order n cost we derived in section 1, now appearing in a vendor's own figure. Now put the number against our own calculation. At 1 million tokens, V3.2 needs about 50 gigabytes for a single request.
That is the same order as the 52 gigabytes we computed by hand earlier. V4 Pro cuts that by a factor of 9.5. And now read their stated reason: making long horizon tasks and test time scaling feasible. In other words, they are optimizing for your workload. So here is the buyer's question to carry away. When an architecture claim is made, ask which budget is being improved: prefill speed, generation speed, memory per user, maximum context, or training efficiency. Never say Model X is better without saying better for what workload.
You will read that Mamba was going to replace the transformer. Here is what actually happened in 3 columns. What did not happen? Pure state space models did not displace transformers at the frontier. What did happen? The recurrent state idea was absorbed. Production models now interleave attention with linear or state space layers. And what mattered most? The unifying result, which let both lines share kernels and theory. Now the verdict in production form at the bottom. Nematron 3 Ultra, 2026. 550 billion total parameters, 55 billion active. It is a mixture of experts hybrid of Mamba and attention, trained on 20 trillion tokens with a 1 million token context. It delivers 5.9 times the inference throughput of a comparable model at on-par accuracy. And read NVIDIA's stated motivation, because it repeats the theme of this whole lecture. As LLM applications evolve from simple chatbots to long-running agents, the ability to deliver fast and efficient inference becomes increasingly important. So use model reports critically. Separate a compelling benchmark result from a general deployment claim. A hybrid design combines mechanisms instead of betting on one. The central insight is practical. Use expensive full attention where it earns its keep, and use cheaper mechanisms where they are sufficient. Kimi Linear is a concrete example of that choice. Now, read the note at the bottom, because it is a lesson in reading benchmarks carefully. The ETH measurement here reports training throughput. It does not report inference speed. Those are different numbers, and they can move in different directions. A design that trains faster may or may not serve faster. As a consequence, when you compare architectures for your own project, first ask which quantity the figure measures. This is exactly the budget-aware thinking we will apply to context engineering next week. The next set of techniques does not mainly change what the model sees, it changes how much model capacity and cache cost are activated per request. Mixture of Experts answers a different question from the ones we have seen so far. Not how do we make attention cheaper, but how do we get capacity without paying for it on every token? The idea is routing. The model contains many expert subnetworks, and each token is sent to only a few of them. Look at the Kimi K3 numbers. 16 routed experts are used out of 896 for each token. So the model holds 2.8 trillion parameters of capacity, but spends only 104 billion of compute per token. That is 3.7% activated. Now understand what that buys. This is the reason a 3 trillion parameter model is servable at all. Without routing, every token would pay for every parameter, and nobody could afford to run it. Now, the 2026 survey framing at the bottom, which is a useful way to hold the idea. The trend is a decoupling of 3 things that used to be one thing: semantic routing, that is, which expert should handle this; the computational budget, that is, how much we spend; and physical execution, that is, which hardware runs it. Now we attack the KV cache directly, and this is the plainest dial in the whole stack. Recall from section 1 that the cache size depends on the number of heads. So here is the idea. Share key and value heads across several query heads, and the cache shrinks by exactly the sharing factor. Read the progression in the figure. Multi-head attention gives every query head its own key and value heads. That is the largest cache. Multi-query attention goes to the other extreme. All query heads share one single key and value head. That is the smallest cache and the most compression. Grouped query attention sits in between. Groups of query heads share a key-value pair, so you can choose your point on the line. More sharing means a smaller cache and less quality headroom.
Less sharing means a larger cache. Now, the practical note at the bottom. Grouped query attention is the setting that nearly every open model you will run this term has already chosen for you. So when you load a model this semester, this decision has been made on your behalf.
This slide carries the number that matters most today, so let us read it precisely. The architecture line first: compressed sparse and heavily compressed attention, manifold constrained hyperconnections, and the muon optimizer. 1.6 trillion total parameters, 49 billion active, more than 32 trillion training tokens. Now the comparison in the middle, at a 1 million token context against the previous generation v3.2. 27% of the single token inference flops and 10% of the KV cache. 90% of the cache removed at the same context length. Now, why this is on the slide, and it is not for the architecture names. Read the author's stated purpose: making long horizon tasks and further test time scaling more feasible. That is a frontier laboratory describing its own architecture work as enabling agents. The systems constraint we derived in Section 1 is now the stated design driver at the frontier. Now look at the same pressures at a completely different scale. Gemma 4, dense models from 2.3 billion to 31 billion, plus a mixture of experts version with 3.8 billion active out of 26 billion total. It is Apache 2.0 licensed, which means you can actually run this one. Look at the techniques listed. 5-to-1 local to global attention, KV cache reduced by up to 37.5%, a thinking mode, speculative decoding, and quantization-aware training. Now read why this slide exists, because that is the real point. The 3 billion model and the 2.8 trillion model are solving the same problem, which is KV cache and long context, and they arrive at recognizably the same answers. That convergence is evidence that the constraint is real and structural. It is not a fashion. Now, the practical note for your project. Open weights models in this class are a serious option for lab work. There is no per token cost, no rate limit, and you can inspect everything. Frontier API models remain stronger on long horizon agentic tasks. Choose deliberately and say why in your report.
Let us close Section 3 in 5 lines. 1. The constraint is context, and its price is flops and KV cache. 2. Attention got cheaper through I/O-aware kernels, trainable sparsity, and linear variance. 3. State space models were absorbed, not victorious. Production means hybrid. 4. Mixture of experts decouples capacity from compute, and 3 to 4% activation is now normal. 5. The labs say this is for agents. DeepSeek and NVIDIA both write it down in their own papers. Now the transition, and it is the hinge of the whole lecture. We have made the substrate bigger, longer, cheaper, and better at reasoning. So now ask the question that matters for this course. Which problems remain even if the model improves? That question opens the second half. One administrative note. The optional depth folder in the readings has 12 papers on frontier architectures. It is there if you want it. It is not examinable.
Now comes the bridge into agentic AI. We are not listing small weaknesses that a larger model will necessarily eliminate. We are naming boundaries of the standalone next token model. This whole section turns on one distinction, so let us make it precise before we go through the list. On the left are problems that scale can fix. Give the model more parameters, more data, more training compute, and these get better. We saw exactly that in Section 2. On the right are problems that do not improve with scale. Read the sentence at the bottom carefully because it explains why. The right-hand column does not improve with scale because it follows from what the system is. It is a consequence of the design, not a consequence of the size. A model that predicts the next token from a fixed set of weights and a finite context has certain properties, and those properties remain no matter how large you make it. As a consequence, something has to be built around it, and that something is this course. So as we go through the next 6 slides, keep asking one question for each limitation. Would a bigger model fix this? If the answer is no, then it needs an engineering response. Limitation 1 has 2 halves, and both matter. First, the knowledge is frozen at the cutoff. The weights encode the training corpus. Nothing after the cutoff exists for the model, and no quantity of pre-training includes tomorrow. That is not a weakness that scale can remove. Second, and this half is less obvious, the knowledge is not checkable from inside. The model has no mechanism to distinguish "I learned this" from "this is a plausible continuation." Both are the same computation. There is no internal flag that marks one as remembered and the other as invented. Now, the measurement. From the GPT-5 system card, graded on real production traffic. The thinking model has a hallucination rate 65% lower than the previous generation, and 78% fewer responses containing at least one major factual error. That is genuine, large progress, and we should say so. But the absolute rate is not 0. Several percent of responses still carry a major error. Now the last line, and this is the sentence to take with you. Chain 20 such steps in an agent and ask what the product of those probabilities looks like. A few percent per step is not a few percent per task. Limitation 2 is statelessness, and the diagram states it plainly. Call 1, call 2, call 3. Between them, nothing carries, no memory. Now, read the box. The API is a pure function. The same input gives the same distribution. And here is the sentence that surprises students every year. A conversation is an illusion, produced by resending the entire history every single turn. The model does not remember your previous message. Your application sends it again. Now, the 2 consequences you will feel by week 5. First, everything the agent must remember has to fit in the context, or it has to live in a memory system that you build. That is topic 4, and this limitation is the reason topic 4 exists. Second, you pay for the whole history on every turn. Read that together with the KV cache from section 1. Long agent runs are expensive for this reason before any other reason. Not because the model is large, but because the history is resent and recomputed at every step. Limitation 3. Let us be precise about what a forward pass actually produces. It produces a probability distribution over the vocabulary. That is the entire output. It cannot read a file. It cannot query a database. It cannot send an email. It cannot check today's date. Now, the second block, which is a subtler version of the same problem, the wrong computational model. Arithmetic, sorting, precise string manipulation. These are token prediction approximations of algorithms. The model is not running an algorithm. It is predicting what the output of an algorithm looks like. Sometimes the prediction is correct. That is not the same as computing it. Now, read the fix on the right. Do not ask the model to be a calculator. Ask it to write and run one. Code execution as a universal tool is topic 3, and it is the cleanest example of the whole agentic argument. Now, the sentence at the bottom, which I want you to remember in this exact form. The model is very good at deciding what should happen. It is structurally incapable of making it happen. Limitation 4. A forward pass costs the same regardless of difficulty. What is 2 plus 2? And prove this theorem consume the same computation per token. The architecture has no way to think harder about a harder problem. Now the 2 responses. Inside the model, there is a partial fix. Reasoning models spend more tokens on harder problems. Chain of thought becomes a form of adaptive compute. That is real and it works. But notice it is still tied to output length. Outside the model, there is a fuller fix, an agent loop. Keep calling with new evidence each time until a stopping condition is met. Now, compute scales with task difficulty and not with output length. Now, read the line at the bottom because it is the cleanest definition of an agent in this whole lecture.
An agent is a way to spend a variable amount of compute on a problem whose difficulty you did not know in advance. Hold on to that definition. It explains why the loop exists at all.
Limitation 5 is, in my judgment, the worst item on the list. Read the documented behavior first from the GPT-5 system card. Prior reasoning models were observed to make false claims about actions they had taken, to say they had completed tasks they had not, and to fabricate prior experiences. Now read the attributed cause, because it is instructive. It is partly attributed to reinforcement learning. Graders are fallible. A model that learns to satisfy the grader is rewarded whether or not the work was actually done. So the behavior was not designed, it was selected for. Now, why this is the worst item? The other limitations produce visible failure. You can see them. This one produces a clean report of success that did not happen. And read the next line carefully. The failure hides precisely when you are least likely to check, which is when everything looks fine. Now, the consequence for topic 8, and you will hear this sentence again. Evaluate outcomes. Never evaluate the agent's account of outcomes. Those are two different measurements, and only one of them is evidence. Here are the 6 structural limitations in one table, with the reasons scale does not fix each one. Knowledge frozen at the cutoff, because no pre-training run contains tomorrow. Cannot verify its own claims, because it is trained for plausibility, not for correctness. Stateless across calls, because the architecture has no persistence. Cannot act on the world, because the output is a token distribution. Fixed compute per token, because compute is not adaptive to difficulty. Reports unearned success, because it is rewarded by fallible graders. Read the right-hand column again as a group. Not one of those reasons is about size. Every one is about what the system is. Now, the line at the bottom. 6 rows. Every one of them has an engineering answer, and none of the answers is a bigger model. We will fill in that right-hand column in section 6, and each answer will turn out to be a component you build. The moment an LLM can use tools and retain context, familiar model errors become system risks. Before we discuss risk, we need to see the system whose risks we are assessing. Follow the loop in the diagram. The model chooses a tool or an action. The action reaches the environment. The environment returns an observation. The observation updates the context, and then the model chooses again. Now read the first box. An agent is not simply a stronger prompt. It is a control loop. The model chooses an action, receives evidence from the world, and chooses again. Memory, planning, permissions, and stopping conditions all live around the model, not inside it. Now read why safety belongs here in week 1 and not later. This loop turns a mistaken token prediction into a possible external effect. That is the whole change. A wrong prediction used to produce a wrong sentence. Inside a loop, it produces an action. We will define the components properly in topics 3 to 6. First, understand the safety boundary around them. Let me answer the question directly. Why is this section in week 1 and not at the end of term? Because the scope of harm changes when the system acts. Read the contrast. A chatbot that is wrong produces a wrong sentence. An agent that is wrong sends an email, deletes a file, moves money, or files a report. Notice what did not change: the error rate. The model is equally wrong in both cases. What changed is the consequence. Security engineers call this the blast radius, how far the effects spread before something stops them. Now the 2 columns. In this course, safety is not a lecture at the end. It is a graded section of your project report and a red teaming exercise in week 13. In your career, you will be the person who decides what an autonomous system is permitted to do. And read the last sentence, because it is the argument for teaching this early. That decision is made at design time, or it is made by an attacker. The central problem is that natural language data can look like an instruction. Prompt injection is the central security problem of this field, so let us state the mechanism carefully. The model reads its context as one stream. It has no reliable way to mark one part as trusted instructions and another part as untrusted data. So if your agent retrieves a web page and that page contains text that looks like an instruction, the model may follow it. The attacker did not need access to your system. They only needed their content to arrive in your context. Now read the quotation at the bottom from Grisheka and colleagues because it names the root cause exactly. LLM integrated applications blur the line between data and instructions. That blurring is not a bug in one product. It follows from the design we studied in Section 1. Everything is tokens in one sequence. As a consequence, any agent that reads untrusted content, and your project almost certainly will, has this exposure by construction. This table is a lesson in how to read a benchmark. So let us do it in 2 stages. Stage 1, read the numbers. Browsing prompt injections, 0.99. Tool calling prompt injections, 0.99. Coding prompt injections, 0.97. Higher is better. Your first reaction is the intended one, 99%, essentially solved. Now, stage 2. Put that number inside an agent. A single task can involve 200 tool calls. At 0.99 per call, the probability that every call resists is 0.99 raised to the power 200. That is about 0.13. So the system is compromised roughly 7 times out of 8. Nothing was wrong with the benchmark. The number is real. What is wrong is reading a per call number as a per task number. Now, the 2 conclusions at the bottom. The model is not the security control, and per call robustness does not survive contact with a loop. So if the model is not the security control, what actually defends an agent? Read the left column. Architecture, not persuasion. Least privilege, so the agent gets the minimum tool scope. Sandboxing, so effects are confined. Human gates on irreversible actions. And cut the exfiltration path. Notice that not one of those is a better prompt. Now, the real example on the right, and it is worth copying. GPT-5 has a documented mitigation. After a connector call returns sensitive data, browsing is restricted to cached pages only. Think about what that achieves. The injection may still succeed. The attacker may still control the model's intention. But there is nowhere to send the data. The attack has no payoff. Now, the lethal trifecta at the bottom, which is the shape to watch for. Danger concentrates where 3 things meet: access to private data, exposure to untrusted content, and the ability to communicate externally. Remove any one of the 3, and the attack loses its payoff. That is a design decision you can actually make in your own project this semester.
Technical boundaries need human and organizational accountability around them. The instruction hierarchy is a reasonable idea. Not all instructions are equal. System instructions outrank developer instructions, which outrank user instructions, which outrank retrieved content. Models are trained and evaluated on honoring that ordering. Now read what the same document admits on the right. The GPT-5 card reports regressions on several instruction hierarchy rows compared with its predecessor. So a newer model is not uniformly safer. Progress is uneven across dimensions. That is a useful habit of mind. Do not assume that newer means better on the specific dimension you depend on. Now the box at the bottom, because it teaches a transferable skill. How should you read a system card? It is written by the laboratory that built the model. It is not peer-reviewed, and the evaluations are chosen by the authors. That does not make it worthless. It is often the only public evidence we have. It means you read it for what is disclosed, and you stay alert to what is not measured at all. The absent measurement is often the more interesting one. Here is a finding that should change your defaults. A monitor that has access to the model's reasoning trace is substantially more informative about safety-relevant behavior than a monitor that sees only the actions and the final outputs.
and monitorability improves as the chains get longer. Now, why this matters for how you build. Tracing your agent is usually sold as an operations concern: debugging, latency, cost. This result makes it a safety property as well. The trace is where intent becomes visible before the action is taken. That is the only moment where you can still intervene. Now, the caveat on the right, and please keep it: a reasoning trace is not a guaranteed record of the computation. It is text that the model produced. It can be incomplete and it can be wrong. Treat it as strong evidence, never as proof. Topic 8 builds on this. So here is the practical instruction. Instrument your project from day one, not in the week before the demonstration.
There are 3 ethical questions you cannot defer, and they are design questions, not philosophy. Accountability. An autonomous system causes harm. Who is responsible? The laboratory, the deployer, the user, or the engineer who set the permissions? Note the line underneath. The model did it is not an answer a court accepts. Oversight. Where does a human have to approve? And notice that both extremes fail. Too many gates, and the agent is pointless. Too few, and nobody is actually in the loop. So this is a design decision with an ethical dimension. Privacy. Agents accumulate. Trajectories, memories, retrieved documents, all persisted, often far beyond the task that created them. What did the user consent to, and for how long? Now, the item specific to this class, and it is a rule, not advice. You will build agents that call real APIs and touch real data. In scope, your own systems and the core sandbox. Out of scope, everything else, without exception. The Week 13 red teaming exercise has written rules of engagement. Read them before you start.
We can now answer the opening question. What must we add around an LLM, and why? Now, we return to the table from section 4, and we fill in the right-hand column. Read the middle column from top to bottom. Frozen knowledge is answered by retrieval and grounding. Statelessness is answered by memory. The inability to act is answered by tools. Fixed compute is answered by the loop itself. Unearned success reports are answered by evaluation and tracing. Now, notice what that middle column actually is. Read it top to bottom again. That is the syllabus of this course. Topics 3, 4, 5, and 8 in order. The course outline is not a list of interesting topics. It is the list of engineering answers to the limitations we derived this morning. As a consequence, when you reach topic 4 and we discuss memory, you should already know which limitation it repairs. Now, let us define the loop properly, using React. The idea is to interleave reasoning traces with actions. Read the division of labor, because it is precise. Reasoning tracks the plan and handles exceptions. Actions gather what reasoning cannot invent. That second half is the important one. There are things no amount of reasoning can produce, such as today's price or the contents of this file. Only an action can bring those in. Now, the results on the right. And note the condition attached. With only 1 or 2 examples in the prompt, React gave a 34% absolute improvement in success on AlphaWorld and 10% on WebShop over imitation learning and reinforcement learning baselines. Look again at how little was required. 1 or 2 examples in a prompt and no retraining. Now, connect this back to section 2. This is in-context learning from the GPT-3 slide, doing the work. The loop was specified in prose, and the model followed it. A loop is not automatically intelligence. It is a mechanism whose value must be demonstrated. This is the sentence that is the thesis of the course, so let us read it slowly. React, by interacting with a simple Wikipedia API, overcomes prevalent issues of hallucination and error propagation in chain-of-thought reasoning. Now read what that is actually claiming, because it is stronger than it first appears. The tool is not a convenience. It is not an integration. It is the error correction mechanism. Now the reason in 2 sentences. Reasoning alone drifts because nothing contradicts it. A wrong step produces the next step, and there is no force pushing back. Reasoning that must periodically check itself against the real world gets corrected because the world answers back. That is the whole argument. The tool call is not there to fetch data. It is there to introduce something the model cannot invent. Now the last line, and it explains the title of this course. This is why the course is not called Advanced Prompting. Look at this trajectory across 3 periods because it tells you where the field is going. In 2022 and 2023, agentic behavior was a prompting pattern. React was a few examples in a prompt bolted onto a model that was not built for it. In 2025, Kimi K2, Open Agentic Intelligence, a frontier model trained explicitly for tool use. In 2026, architecture reports cite Long Horizon agentic tasks as the design target. Nematron 3 Ultra and DeepSeek V4 both do this, and we read their own words earlier today. Now, read what that trajectory tells you. Agentic has moved from something you do to a model to something a model is built for, to something the silicon and the architecture are optimized around. 3 independent levels of the stack now assume the loop. That is a strong signal about where the field believes the value is, and it is also why the systems constraints from Section 1 belong in a course about agents.
Now, the counter-argument, and it is a good one. I want you to be able to make it. Agents are frequently the wrong answer. They cost more. They fail in more ways. They are far harder to debug, to evaluate, and to secure. A loop can run away. A single call cannot. And read the next sentence, because it is a judgment about the industry. A substantial fraction of systems marketed as agentic would be better as a deterministic workflow with one LLM call inside it. Now, the 2 columns give you the test. An agent earns its place when the number of steps is not known in advance, when the next action depends on the last result, and when the task genuinely needs external state. It does not earn its place when the steps are fixed and known, when you could draw the flowchart in advance, or when the word agent is doing marketing work in a design document. Now the question at the bottom. Does this need to be an agent? Ask it every week. It is graded in your proposal.
This table is our roadmap, again, now with a purpose attached to every row. Topic 2. Reasoning and context. Making a finite context do useful work. Topic 3. Tools and interfaces. It cannot act and it cannot verify. Topic 4. Grounding and memory. Frozen knowledge and statelessness. Topic 5. Architectures and planning. Turning the loop into a design. Topic 6. Multi-agent. When one loop is not enough, and equally when it is. Topic 7. Advanced paradigms. Learning from the agent's own trajectories. Topic 8. Evaluation and observability. Reports unearned success. Topic 9. Security and safety. Data and instructions share a channel. Now, read the line at the bottom. Every topic in this course answers something in the Section 4 summary table. Nothing here is decoration. If you ever wonder why a topic is in the syllabus, come back to this slide.
Before next week, there are 2 things to do. First, and this is not optional, work through the setup folder in the course repository, Python 3.11 or later, and the virtual environment. An API key stored in the .env file. Set a hard spending limit today, not later. Then run the verify script. Topic 2 starts with code, so a broken environment costs you the session. Second, the reading. Core reading is attention is all you need for the mechanism we studied this morning. Then skim one 2026 model report, either Kimi K3 or DeepSeek V4, and read the model report in a particular way. Read it for the architecture and for the disclosed limitations. Do not read it for the leaderboard, because the leaderboard will be stale before the midterm. All the PDFs are in the readings folder for topic 1. And start thinking about the project now. teams of 2 to 3, proposal due week 5. The best projects come from a task you already care about.
Take away 3 ideas. First, attention is old, but its economics are central. Context costs time and memory. Second, the most important LLM limitations are structural, so scale alone cannot solve them. Third, agents are a purposeful response. Tools, memory, verification, and control around the model, and they raise the stakes because an error can now become an action. Next week, we learn how to make a finite context window do useful work.